Hello, everyone. Thank you for joining us on this webinar. So I'll give it maybe a minute or two to let people come in. So let's get started. Today, I'll be going over this topic with you. So we'll talk about how to select your spectral band, so short wave, mid wave, long wave when doing infrared imaging. So how to choose and what's the advantage of each band. So first of all, I'd like to do a little poll with you. So I'll launch this, just have a rough idea of what we have in terms of experience in our audience. So how would you rate your knowledge in terms of infrared imaging? So just click on your answer. Well, it's going to give us an idea of what kind of expertise we have in the crowd. So I'll give a maybe 30 seconds. So this webinar is really made to be accessible to everyone. So even if you're very much a beginner, that's perfectly fine. If you have a big experience, it can be very interesting to talk about the comparison between those different spectral bands. Okay, that's interesting. So a good portion of the crowd that does have direct experience. A few, one or two maybe, that do have a thermal imaging expertise, I would say. That's great. And then quite a few of you that don't have direct experience but are interested or are considering the technology. So welcome. That should be interesting. So if you have questions even during the presentation, feel free to write your own questions in the question box in the GoToWebinar tab that you have there. And otherwise, let's get going. So before I start, I just want to mention that this is part of an ongoing series, so the Essential Guide to Infrared Imaging. I did the first part as well. So I'm Antoine Dumont, I'm a field application scientist. Got my PhD at the University of Toronto, and in material science, yes, in optoelectronics, and then I transitioned to work for Telops afterwards. And it's very interesting. We have a lot of interesting people working for Telops and have a lot of research and development happening that are very interesting. So today, let's jump on, let's jump on onto our topics. So short, mid, long wave, how should we choose? So I'll give a very brief introduction to Telops, but I did go over that quite well in the first part. So I invite you to take a look at the first webinar in this series that talk about speed measurements, so high speed measurements. After that, I'll go over some radiometry background to understand how to do that selection for your spectral band. And then we'll talk really about the short wave, mid wave, long wave imaging. What's the difference? What's the impact on the scene for your imaging? What's the impact on your spectral band when you decide to do your measurement? Then we'll conclude with a few scene comparisons that are using the same scene, but different spectral bands looking at the same thing. Yes, so Telops was founded in 2000 in Quebec City. We do employ nearly 100 people that are mainly in Quebec City, but we have a team in the US and in Europe, in Paris. We really strive to establish ourselves as world leaders for infrared imaging solutions, and we do offer the fastest infrared cameras on the market. And as of last year, Telops is part of Exosens group. So Exosens really strives to basically cover the whole electromagnetic spectrum. So we're now in contact with great sister companies that work in different part of the spectrum, and we're expecting great growth and interesting developments from that. We offer a multitude of products. So we have the hyperspectral camera on the top left here. That won't be the focus of today's talk, although the selection of the spectral band is still relevant to hyperspectral cameras. But I'll focus mainly on data and images that were obtained with fast cameras and multispectral cameras. So we have the multispectral camera, which is sort of an in-between hyperspectral and just broadband cameras that we have here, with multiple filters that are spinning to do an acquisition with different spectral windows simultaneously. We have the spark cameras, which are like the broadband cameras, but more entry level that go not as fast, but still offer a great radiometric accuracy. And we have high dynamic range cameras, especially a new one that I'll talk about a little bit. And of course, modules that can be used for easier integration in systems. So we're in contact with research group, industry that touch a lot of different applications. So of course, infrared cameras, there's a lot of ballistic defense applications, but there's also some interesting research in combustion analysis, experimental mechanics, gas detection, and mineral identification. That's generally more in the realm of hyperspectral imaging. It's still possible to do that in some way with multispectral cameras. And then IR signature, looking at a specific heat signature with the broadband cameras. Additive manufacturing is very much a growing field, growing market as well for infrared imaging. And then there's non-destructive testing, so testing materials, boards, wafers, electronics, all that kind of stuff, detecting defects and cracks, that kind of stuff, without actually touching the material. Now, when we're talking high performance fast cameras, I mentioned Telops is very much a leader in the market for these kind of high grade scientific cameras. We offer different kinds of broadband cameras, so covering the whole infrared range from short-wave, long-range, mid-range, mid-wave cameras. But it can be confusing if you're starting in the field, or if you only know one spectral band, you only know one kind of cameras, where to go if you have a new application, if you're interested in another kind of infrared imaging, how to choose your camera. And there's a bit of a sea of options when you're looking at another camera that you'd be interested, or a new camera. Here we're just talking about mid-wave camera, and there's already quite a few, plus the new one, the M2K UD, that was just released, which offering a good balance between spatial resolution and speed. But then you start looking at the rest, and there's the HD, there's long wave, very long wave, fast SWIR, S1K, which is short wave as well. And that doesn't even, that's not even including the sparks or the multispectral cameras. So there's a lot of information out there in terms of what's available, and trying to go through all those parameters, all those spec sheets, what's the best for your specific application, understanding what's best in terms of spectral band to choose. It can be a bit overwhelming. So I'll do my best to go over that with you today. Not one camera at a time, but the different advantages and the properties of different spectral bands. So we'll go over a bit of radiometry theory. So nothing too complicated, don't worry. But it's good to understand those principles when you're interested in infrared measurements, of course. So the electromagnetic spectrum is what we see here. So we have the whole spectrum, so going from gamma rays to radio frequency, and we have our little infrared window just in the middle here. In, let's say, physics, chemistry, science in general, common definitions are typically what we have here, going from near to far infrared. Often what we see in science papers, science articles, when we're in the infrared industry or remote sensing, typically separate it a little bit differently, and particularly to avoid the transmittance void window for the atmosphere. So we have nothing between the 5 to 7 microns, and that's on purpose. So you can't see much in that window. So we have short wave 0.7 to 1.4, mid-wave and extended mid-wave from 1.4 to 5, then long and very long wave going from 7 to 12, 13 microns. That's typically when you're looking at infrared cameras, and I'm not just talking Telops camera, but infrared cameras in general. That's typically the jargon that's used. Now, If you have any physics background, this is probably familiar to you. So we're looking at Planck's curve here. So when any object is at a specific temperature, it will emit infrared radiation, or I should say radiation in general. If you get very, very hot, like the sun, and you can see that your emission will be peaking in the visible spectrum. So that's why we can see very well when the sun is out. Now, when we're using infrared cameras, the data that comes from the camera, it's important to understand we're not looking directly at the true temperature, the real temperature of an object. It really is a radiometric temperature or radiometric radiance energy coming to the detector. And that difference is critical to understand when choosing your camera, choosing the spectral band of your camera. So the first thing to understand is that Planck radiation. So the temperature of an object will emit at a specific wavelength that's peaking at a different wavelength depending on the temperature. So you can see that the peak of that wavelength will go towards the right, so longer wavelengths when you're colder in terms of temperature. So something that's around room temperature will be emitting much more radiation in the long or very long wave infrared. So all of this, those are curves that are valid for perfect black body radiation. What's a black body? I'll go over that a little bit more in a slide. But materials are never perfect emitters. And so that's why there's an extra level of complexity when considering radiation for infrared imaging. So a little note here, when what room temperature, so 293 Kelvin, it only emits about 1.1% of its energy in the mid-wave band compared to 42% in the long wave. So we can see we'll be much more sensitive to a body at room temperature in the long wave compared to mid-wave. But so understanding the difference between a radiometric and true temperature, that's where we need to bring in emissivity. So at that given temperature, so there's no object, no body that really emits perfectly like those curves that I just showed. So that's where the emissivity is a parameter that basically impacts how much radiation is emitted depending on the temperature and the wavelength and the surface of the material. So just roughly, it's affected by all these factors, especially the wavelength and the surface of the material. Typically, the materials come with a constant in terms of emissivity, hopefully within a spectral band as well. But the general rule is when you have a polished metal, those are really, really good reflectors. So they will be reflecting light very, very well from the environment, from a source that's not the material itself. If you have a perfect black body would be an emissivity of 1. But like asphalt, glass, human skin is a very high emissivity as well. Those are good absorbers. So they will be emitting radiation depending on their temperature directly more than reflection. Now, to have a good idea of what it looks like, that's the kind of emissivity spectrum that you can get. So you can see that the radiance of, in this case, those are different minerals, differs very much depending on the wavelength. So if you're at 9 microns here, you're at 0.5 emissivity. If you're at 11, you'll be very close to 1. So the radiance will, the temperature or radiance that you see in the camera really depends on your spectral band and where you're at on that spectrum. So you can see that that red line is really what a black body would be. But then you have a quartz, which is really what a more normal real material would look like. Okay, so that was just a brief overview of radiometry. I don't want to go over too many details of that, just to understand a little bit why it's not super straightforward when you need to understand how to select your spectral band. So when you do your selection for an infrared camera and the spectral band dedicated to that camera, you do have to understand what kind of material are we targeting, and what is the environment you're doing the measurement in. If you have high humidity, a high concentration of CO2 and dust, then that can impact how well you can see your target or through that atmosphere. Mid-wave typically will see better in those conditions compared to long wave. If you have an environment that is outside, then illumination like the sun can have a good impact on what you're seeing with your camera. If you're inside, what kind of illumination do you have as well? Otherwise, if you know that you're doing infrared measurement for a phenomenon that is happening at a given wavelength, like gas absorption or gas being emitted through combustion, then of course, I barely have to say that, but of course you have to go within that spectral band of interest. If you're really looking at a temperature measurement, that's where you have to take into consideration all those radiometric factors. And so the radiometric temperature that's expected, without having to know it very specifically, having a rough idea if it's very high or very low, that will indicate which spectral band you would probably have to go to. So we have the different spectral bands here with the atmosphere transmittance spectrum that we can see here. So we can see that there's no transmittance between 5, 7, 7.5. And then it varies quite a bit from wavelength to wavelength, like I was saying, for the emissivity. So that's a combination of all those gas molecules in the atmosphere. All right, so let's go and talk about our different spectral bands. So let's start with shortwave. With the Telops cameras going from 0.9 to 1.5 microns. When we're talking about shortwave imaging, it typically is light that is mainly captured through reflection. So we can see an image here. It looks quite nice. High intensity, if you were to look at the temperature on that reading, it would be 300, 400 degrees Celsius. Obviously, that's not the real temperature of those leaves, of the grass in that scene. It's telling us that temperature because it's light coming from the sun. So all that strong radiation coming from the sun being reflected on those surfaces can give us a good infrared image, can give us quite a bit of information about the light, how the light is reflected and absorbed by a surface. So that's why that's very interesting for multitude of applications like food inspection, forest monitoring, like a canopy that is in direct contact with the sun, different material analysis. All of that can be done through shortwave quite well, as long as you have a good source of illumination, either in a lab, on a belt with a good illumination, or if you're outside, the sun is always the best illumination, I would say. If you want to do actual thermal imaging in shortwave, then that's where you require extremely high temperatures. So we're talking welding, explosion or ballistics, even plasma physics sometimes, going up to those high temperatures. So I have two examples here of a battery explosion. So that was taken with shortwave, so an S1K, where we have that high temperature, that high speed, high temperature phenomenon, or a cascading failure of a battery. Those tests were very interesting. We have an actual webinar that was done on the topic. If you want to see a lot of explosions and interesting battery research, feel free to go take a look. Also, here we have a welding video where we have that high temperature welding point. People are very interested in understanding the temperature and the behavior of the material at that very specific point where we have that contact and the high temperature. So if you can have a good understanding of the melt pool temperature and the behavior over time, that can be very good for welding research. But there's also something interesting in shortwave imaging where it offers a unique window that's transparent for silicon. So that's very useful for semiconductor inspection. You can detect defaults and cracks in your electronic boards, semiconductor wafers. You can also see through glass in that spectral band. So that's very interesting for non-destructive testing, where you can see through material that's typically not transparent in visible or other infrared bands. So that's an actual brick of silicon where you can see very well through it. So seeing that hand through it. That image comes from our sister company Xenix that focus on shortwave cameras and longwave cameras, different from Telops, but very good products as well. And we have electronic board inspection. So that's a resistor that was imaged through a board like this with a camera. Now for midwave imaging, more in the 3 to 5 microns for the standard midwave, I would say that band is the most versatile really of the different ranges for infrared imaging, because it's in that middle. We can see quite well room temperature objects all the way to high temperature events, because we have that flexibility with those cameras. So being that in between range, you can actually do combustion analysis, experimental mechanics, like on the right here, where we had that PLC effect in a tensile test that was done in Germany at Fraunhofer, where we have a tensile test. So it's a high speed measurement. We have a tensile test that starts at room temperature. So it's important to be able to still see the object. But then it heats up due to dislocation in the material and can get quite hot, especially at the failure point. So that's a good example of an application. The other one on the left here is cold spray. So a lot of people are interested in this growing field where we have warm particles of an alloy. In this case, it was a copper alloy. But being able to image those particles in flight, going extremely fast, around Mach 2 in terms of speed. But the temperature, the real temperature of those particles is around 500, 600 degrees Celsius. So very high, which technically would be possible in shortwave imaging as well. But because they're going so fast, and because they're made of a metallic alloy, so low emissivity, the temperature that you get in your camera is much lower, around 100 and 120 degrees Celsius. So that's why midwave camera going in the longer wavelength is able to get that radiance and have a better contrast compared to shortwave imaging, which wouldn't be able to show any kind of image for this. The stretching of those particles also lowers the temperature that each pixel is indicating. So that's why there's an extra level of processing that has to be done when you want to get to that real temperature of your object for this kind of blurring image. So experimental mechanics, cold spray, which is part of additive manufacturing. Fluid dynamics is also an application that's using those kind of cameras. But we're talking 3 to 5 microns here. It's possible to extend that range to 1.5 to 5.5 microns to offer a bit more versatility. So going closer to shortwave, where you would be actually able to see through glass with the extended midwave cameras. But it also allows a higher sensitivity when you do multispectral measurements, like water vapor and hydrocarbons. So we can see here, we have those H2O bands, where midwave does touch a little bit of those H2O absorption bands, but with the midwave extended, it offers a lot more response, more signal from H2O. So for this kind of experiment where we had a combustion, where we had natural gas being combusted, yes, we have that H2O and CO2, that is the natural products from that combustion that are visible here. But this research group in Spain were looking into having a greener process. So having a hydrogen combustion instead of natural gas for their ceramic. And then we can see that we have a very clear image of H2O being emitted, H2O vapor, which is still very, very hot. And no CO2 is detected at all, which is exactly what was hoped for during a hydrogen process, which theoretically doesn't produce anything apart from H2O. Now, when we're doing multispectral measurements like this, the filters that are used will create a narrower spectral window. Now, that narrower spectral window, where it be in mid-wave or long-wave cameras, because you're narrowing the spectral radiance that's coming into your camera, the minimum temperature of that window will have to increase as well to get a higher amount of radiance into your detector. So that's important to understand as well when you're doing that kind of measurement. Possible to use filters on non-multispectral cameras, sorry, spectral filters on non-multispectral cameras to have a good image of something, so H2 in this case, or CO2, if you want to look only in one window at that phenomenon. But you won't have the possibility to have that simultaneous view of all those different filters, including broadband. Now, in mid-wave imaging, there's a higher demand in the cooled scientific camera market for this. So, of course, there's a bit more of a push for innovation and variety. That doesn't mean that the short-wave or long-wave cameras are not as good. They're still very interesting and offer the same high radiometric accuracy. But when we're talking mid-wave cameras, there's a bit more of a higher selection or variety for that range. So we have up to super HD cameras at Telops, which allows non-destructive testing and resolutions that were impossible to obtain before. So incredible images, like that little speck here on a metal bar, which looks like only a pixel from far away, but you can see there's a 20 pixels on that little point here using the Super HD camera. So it allows a much better analysis of a surface or of a scene using that Super HD detector. There's also the new high dynamic range cameras, which offer incredible images. So that's really a revolution in terms of technology in the infrared imaging field. These cameras offer an extremely large range of temperature within a single frame as well. So 0 to 800 degrees Celsius within a single exposure time. So it's a different way, a different architecture for the readout integrated circuit. There's an interesting webinar specifically on that camera if you're interested. Just showing the diversity of mid-wave cameras that are offered at the moment. Now, in long wave, that's really purely thermal. So in the mid wave, we had that in between emission and reflection sometimes in mid wave, depending on the materials you're looking at. Long wave imaging, we're really in thermal because in room temperature, you'll be able to have a very good sensitivity at those lower temperatures. So these cameras are particularly useful for industrial maintenance inspection. So you can see a small difference of temperature or those cracks or material defect on the surface, which would create a small difference in temperature, the way the radiation comes from that surface. And therefore, it can be very useful to do those measurements with long wave to get those early detection before any kind of failures occur. We had that video of the wheel spinning here. So it's still low temperature, it's in a colder environment. And you can still see there's a non-uniformity that occurs during friction, during that braking of the wheel, of the brake disc. And that can be useful when testing parts like this here. So that red line that we see on the edge doesn't remain the same everywhere. So there's a higher friction due to the brake pad, the disc being non-uniform. Of course, we're talking lower temperature, room temperature. So medical imaging can really use those cameras. They need low temperature with higher sensitivity and a good resolution as well. So we have two body, or let's say organic body part images here, where we have a cancer cluster that was implanted into an embryo here, that was imaged to see the difference in the metabolic rate of those cancer cells compared to the rest. And then we have a good resolution image here with an eye, eye being closed, that you can actually see the small difference of temperatures around the eye being closed. Very useful for different kind of measurements in medicine that do require that sensitivity. Of course, for surveillance and quick detection threats in military or defense applications, those are the ones that are the most sensitive for body heat as well. So very interesting to have those long wave cameras offering that higher sensitivity. I mentioned that the multispectral cameras can be used for long wave cameras as well. So some materials do have stronger features in terms of their spectral signature in the long wave. A good example would be minerals. A lot of minerals for mining applications do have strong signatures in long wave. Now, I talk about spectral signature. Of course, it's easier to really identify with a hyperspectral camera where you have the full spectrum. But the multispectral cameras do offer the discrete separation of those spectral bands in long wave, and you could identify some minerals that way as well. Now, talking about cold temperatures, we're in Quebec. So in the middle of the winter, we're looking at power line for looking at the temperature, inspect parts, seeing how it's if it's doable at those negative temperatures. And we can see those power lines and those power lines temperatures being very accurately represented with the Telops cameras as well, all in the negative temperatures, all in Celsius, obviously. But with the long wave cameras, it allows those kind of measurements that are impossible with the midwave or, of course, shortwave. So let's take a look at some scenes. My colleague Joe Carrick in the US had the opportunity to do a measurement with 3 different cameras on the same scene. So here we have a heating tower, so with a flame in the middle, typically used when it's colder, not 30, 40 degrees outside. But we have different materials, and we have a tree with leaves in the background. So we have all those different materials that I mentioned with 2 sources. So we have the heater emitting a good source of infrared, of course, with the flame, but there's also a lot of radiation coming from the sun being outside. So we can compare what we're observing with the different cameras. So taking a quick glance at the different images, it's clear that with the shortwave image that we have here, we can see the flame very well, and we can see the flame moving in that glass tube that is inside the heater, which is not the case in midwave and longwave, where the glass is almost fully opaque in midwave, so it looks like just a warm surface that's emitting heat. And in longwave, it's too hot, it's even saturating at that point. In shortwave, we have that typical reflective image from the trees, the leaves in the background, with a good resolution, being able to see the features quite well. Same thing for the plastic here, that is that smooth plastic surface, typically a highly reflective material as well. And so we can see reflection from the sun, and if you were to look at the pixels a bit closer, reflection from the heater as well. The rest of the objects are fairly uniform. Typically, that's what you expect from shortwave. Of course, the temperature that we see at the bottom is not the real temperature unless we're looking directly at the flame, which can go up to 600 degrees. But the rest is the temperature through reflection of the sun radiation. Now in midwave, to try to avoid saturation, we need low exposure time. So it gets quite noisy. We have that temperature on the heater glass bar, but we don't see much. We don't see anything, the features in the background. There's not much coming that's warm enough being emitted in the background. And the other objects around are all very close in terms of temperature. Similar emissivity, but they're all very low temperatures, so the contrast is difficult to see. But when we look at long wave, then it gets a bit clearer. So we go back to having features in the background. The long wave allows us to have more features, a better resolution, better contrast with room temperature or outside temperature that are the leaves. And then we have the heater being mainly all saturated, but we're able to see water vapor, CO2 being emitted around the top of the heater as well. So we have those different points that are different from one band to the other. We'll take a closer look at, let's say, the temperature that we're measuring in this case. So with the hot target being the flame, we can see that we have that 650 degrees Celsius. We have the glass being fully transparent in shortwave. We have also the reflection on those metal poles that we can see right here, going higher than the background. For midwave, we're basically plateauing when we're not using a filter to 200 something degrees Celsius, which is the temperature limit when we're not using a filter. So what we can do is put a filter in front of our detector to lower the radiance coming in our spectral band uniformly. So you don't affect the emissivity change from the different materials, but that basically blocks anything that has a low temperature from your image. So everything becomes black unless you're at 160, 170 degrees Celsius, which is why we have a lower intensity light coming from the heater in this case. It's still close to the temperature we were having there. We can see that it's just a little bit higher. So that's why we needed that switch to the neutral filter in midwave. Long wave, you can still apply a filter and apply some denser filters to have those higher temperatures, but you don't see as well compared to midwave, especially shortwave. So when we look at the top part of the heater, where we can still see some of that smoke happening in midwave using the neutral filter or not, we have that high temperature aspect. We knew that the temperature would get up to 600 degrees Celsius with the shortwave, but that neutral filter that looks like it's taking away a lot from your scene is still plateauing when you're looking at the hottest part with the midwave. So it's a very hot target where we can play around with the filters in midwave, where you have the possibility to get those warm targets. But the shortwave will tell you a direct measurement without blocking the background for your hot target. Now, just a quick glance, but you can see in shortwave, it was basically impossible to see those vapors coming out of the heater because they don't have, it's mainly transparent in shortwave. Now looking at a cold target, we had a block of ice on the right here. And so of course, shortwave, that block of ice is lost in the noise. There's a little bit of reflection from the sun, but it's not much different compared to the rest of the background. When we compare midwave to longwave, then we can see that the temperature in midwave of that block of ice doesn't go to where you'd expect it to go. We go all the way to 20 degrees Celsius, and the barrel underneath is around 40 degrees Celsius. It shows that for low temperatures, midwave really has a hard time with that contrast. But when you go to long wave, that's when we go to pretty much 0, 1, 2 degrees Celsius. And you have that sensitivity going from the ice to the barrel, showing that contrast. I still show that that barrel is at the same temperature from what we're measuring in midwave. So it shows that that is the radiometric temperature that is expected from that barrel. I don't have a shortwave image, but basically I was talking, it's basically lost in the noise of the rest. On that specific spot, it's saying it's 300 degrees Celsius. It's pretty much just a reflection and mix in the noise of the background in that band. Another great scene comparison that I wanted to talk about is this work that was done at the Louvre in Paris. So research center for the for repairs and taking care of artifacts and paintings, yes, in France. Collaborated with Telops with a midwave and longwave camera. And they used a process that's a little bit more advanced than just doing imaging. So you can do pulse thermography So we have two different flashes that will send a pulse of infrared radiation. And then you measure that reflection and the emission coming from the paintings, depending on the heat that remains or that's being dissipated in the different layers of the paint and the textile. So we have a comparison here of the first painting. So it's called La Bohémienne. It was a replica, so that's why they added little splotches of paint and little traces here and there to do that first test. And you could see that the paint pigments are still quite visible in mid-wave, whereas they're practically invisible in long wave. I will mention these are phase amplitude images. So the image that we see here comes from a Fourier transform as well, due to the different frequencies that the pulses were used at and the measurements as well. So what's interesting is with that comparison of the spectral bands, you're actually able to see different features and see different layers in your painting and see the textile behind it. You can see crayons and pencil marks behind the painting. You can see the thickness of different layers of painting using the frequency and the different spectral bands. And the other painting, which is a real 19th century painting here, doing that process, they were able to realize, they were able to see that there was that feature that wasn't visible here or in midwave, where we have a, it's called basically a pentimento. So it's a feature, they think it's a church that was in the painting, that the original painting did have, that the painter added that at first, but then that painting was revised and reworked decades later. And basically that was removed, and they painted on top and added that village basically instead of the church. Not only that, but you can see strains in textiles, you can see other marks and the preparation layers on the textile, comparing the midwave and the long wave images on this target. So it's really interesting. So that combination of different spectral bands offering a way to do non-destructive testing to compare that the material properties and material status, basically the state of the different layers in this case. So that's it for the webinar. So in terms of key takeaways, I want you to remember that each spectral band is crucial for their specific applications, and depending on your temperature and your materials, you need to select them carefully because they all have their own advantages. You can combine them when it's possible to really get a full picture of the data, like the scenes that I was talking about in the last few slides. But high temperatures is possible regardless if you're in shortwave, midwave, and long wave. You just have to add some filters, and that will affect what you see for the rest of your scene. Low in ambient temperature, that's more in the realm of long wave, still possible in midwave, especially if you're remaining 3 to 5 microns, but the high sensitivity really is in the long wave. So every material does have a unique response to the transmission and and absorption of infrared emission. So it's essential to have an idea of what kind of material you're talking and what kind of radiometric temperature to expect when you're deciding to use your camera for a scene like this. So these are just a few of our collaborators with whom we did some of those data measurements. If you have any questions, please write them down here in the question tab for the GoToWebinar window. And thank you very much. All of these webinars will be accessible on Telops, so they are recorded. So if you have a question now or later on, feel free to write to us at sales@telops.com or on the Telops website directly. So thank you very much. Okay, so let's take a look at some of the question. So will there be an auto capture of the verbatim? Yes, there'll be a closed captioning of the webinar as well, make it easier for anyone and our international customers and or people that are interested. So that's not a problem. Yeah, still showing the poll results. That was taken care of. Anything with exposure times in the 10 to 20 nanoseconds or better range? That's a good question. We do get that often, especially when comparing high-speed visible cameras to infrared cameras. Infrared cameras, we're talking about a few decimals of microseconds. 10, 20 nanoseconds would be very, very difficult. I don't think it's possible at the moment that you could talk with our R&D team to discuss the possibilities to push the electronic to that point. But for the moment, with infrared detectors and integrated circuits, I don't think you can do that, at least not very easily. So we have a question here about application with semiconductors, where layers of a device are infrared transparent to some degrees. So silicon is indeed transparent for shortwave. Need to accommodate a wide variety. A wide variety. One away. Ultra-wide bandgap semiconductors as well. Is there a way to evaluate and calibrate for the effects of the transparent layers on a temperature reading of a buried device? Yes. So it's basically you have to build a radiometric model. So understanding the radiometric temperature coming to your detector versus the true temperature, there's all those layers of either the atmosphere, material, gases, and in this case, semiconductors, that will have an impact on the radiance from the target coming to your camera. So if you're able to have a transmittance spectrum or transmittance even measurement, that's even better, of your materials, or each individual materials, or even your sandwich of semiconductors, having an understanding of the transmittance of those materials that are on top of your target, and then doing that modeling of understanding how much of that radiation will be absorbed and or transmitted towards the atmosphere and then towards the camera, then it can give you a good idea of what you can expect in terms of infrared measurement. Ultra wide bandgap semiconductor, that could be tricky. Depends on the material. You would have to look into the transmittance window and what kind of radiation is absorbed and or transmitted, depending on all those semiconductors that you're talking about. That's a very interesting question. Feel free to contact me directly through Telops, and then we can discuss a bit more maybe about that. Another question here: how to manage to convert radiometric temperature to real temperature? Well, that's a question. The quick answer is knowing your transmittance window, your transmittance spectrum from your atmosphere or materials or gases in between, and knowing the emissivity of your target. Those are the two big factors. If you're just looking at an experimental measurement, that is your camera looking straight at a warm target, let's say the tensile test in the experimental mechanics data that I showed, it's pretty straightforward. There's nothing interfering much with the radiation between the object and my camera. So if you have a decent idea of the emissivity of your material in that spectral band, so that's important to know if it's mid-wave, long wave, short wave, you know the general averaged constant emissivity in that spectral band, then it's just a ratio, and approximately a ratio, and you'll increase your temperature from what you're seeing. That's usually how it goes if the atmosphere is room temperature or around that. So if you have an aluminum sample, you're looking at the camera, it's heating up, with your camera, you're seeing 60 degrees Celsius. Emissivity is quite low, 0.2, 0.3. You can actually input the emissivity properties in the Telops software to have a rough idea at first. And that will increase the temperature by a factor corresponding to the emissivity percentage. So we'll increase the temperature by, in this case, a factor of maybe 3 approximately. Is it available to have a booklet to get the R basics as you presented? That's a good question. There are series. The webinar will be available as a PDF file as well. A direct booklet. That's a good question. There are a few explanations about the infrared imaging on the Telops website. Maybe not a direct booklet, but that's certainly something to consider. So thank you for that question. All right, there's a few more questions. I'll grab maybe one more and then I'll answer the rest by email in the next 24, 48 hours. So I have one question here for autonomous driving perspective. Most of the current work is in long wave. What's your take on that and how can we benefit in autonomous vehicle perspective using mid-wave or short-wave? That's a great question. The long wave is essential for self-driving cars because that's where you have the most sensitivity for humans and for room temperature objects that typically we find on the road. So that it makes sense. For mid-wave and short-wave, I would say short-wave is interesting because it offers another kind of machine vision for that system, offers that reflective aspect that you really don't have in long wave, and that you can still see very well features that are not visible in long wave, like we saw with the previous slides. Mid-wave, I don't know if you need mid-wave for self-driving cars because it's in that in-between, but it could be interesting depending on the signatures of targets that we're looking at. So if we're not talking about human beings, surfaces or vegetation, if there's some accident, there's some fume, there's some dust in the air, atmospheric hazards, that kind of stuff. In that case, maybe mid-wave could be interesting to be more transparent in that aspect. You can see more through that dust or high CO2 content atmosphere. That's something to be considering in that case, I would say. But you'd have to understand all the parameters that are happening, and there's a lot, I'm sure, that's happening. Self-driving research. So I would say mid-wave maybe more for that kind of atmospheric compensation. Yeah. Okay, well, that's loads of really interesting questions. We'll take the rest and try to answer those very soon, I promise. So thank you very much for attending, and I'll see you all hopefully on the next part of this webinar series.